Before we dive into the fascinating details of this galaxy and the images, let's take a quick look into how anyone with a computer and internet access can produce these same stunning images released by NASA. Since all data on the repository, known as MAST, the Barbara A. Mikulski Archive for Space Telescopes, or MAST, is public access, it is freely accessible to all and no account is required. Okay, this is a brief description of the account users' responsibilities and creation of accounts, etc. We have an account here at Astronomy for Change, but it's not required. Okay? Alright. The only caveat is that some of it may not be part of the early release observation program, and thus that data won't be available until 12 months from the date of observation. Let's first check out this site, its features, what is available, and how to access the data. Then we'll briefly go through the pre-processing steps in PixInsight in order to produce that first raw image that we refined and honed to produce your first amazing image. From James Webb, from Hubble, from any observing platform, orbiting observing platform, available here on MAST. Okay, so the first thing we want to do is we want to select a collection of data, images and data, from which we will download and process our image to produce the download and process the data to produce the image. Okay, so here we want to choose JWST instrument keywords. Now we chose NIRCam, the near infrared camera, but the other available suites include MIRI, NIRIS, and NIRSpec. Their names are kind of self-descriptive. We get a sense of what they do just by their name. Okay, so NIRCam, let's take a look at data available in NIRCam. But now we have to choose an object. We have to choose our object of interest. We click Advanced Search right here, and that's going to open up another dialog. We have to make some additional choices to get to the data. One of the most important parts of this is the choosing the correct filters. Right, in these images and analysis we did for NGC-1365, we chose the 2 micron filter, which is f200W. We chose the 300 or the f300M, which is the 3 micron filter, and the 360, the f360M, which is the 3.6 micron filter. So the images, the data, the wavelengths of light were at 2 microns, 3 microns, and 3.6 microns. So these images, this is not how it looks to the eye. These are not visible light images. These are all infrared images. Everything we're going to see, everything we're going to talk about pertaining to this galaxy, all these images, these fantastic, stunning images, are in the infrared. Okay, there's no color per se in the infrared. And we're going to get into how we produce these images using the standard RGB processing format. Okay, we produce gray tone images in each waveband in the 2 micron, 3 micron, and 3.6 micron wavebands. We produce 3 grayscale images and combine and integrate them to form what they call a composite image. And the colors get assigned internally in the processing program. Okay, so that's a step that comes later in this process. But for now, the filters that we chose were the 2 micron filter, the 3 micron filter, and the 3.6 micron filter. Why do I say that? Because that's all that was available. When we go back and make our choice, you'll see what I mean. So you have to display all objects available, whether it's in the early release program or not. They give you everything here. Okay, so these are all the targets that the telescope has observed thus far. Now we're going to scroll down here to find NGC. Here's M33, the great galaxy M33. If we choose this is not part of the early release observing program. So all the data and images you'll see if you open this up would have a padlock on it. It won't be available for 12 months from observation. Okay, so we're going to come down here. We're going to scroll down until we find NGC-1365. And we'll open that up and we'll proceed from there. Here's M16. This is a famous image that was presented, I believe, as part of their the ceremonies back on July 12th. M16, Messier 16. All right, so we're going to keep scrolling. This one I checked out already. NGC-891 is a famous Edron galaxy. Okay, very interesting study, but again, it's unavailable for 12 months. Here's NGC-1365. This is our object of interest. So we click this, and then we come back up here and click search. Normally, what you could do is choose the filters you want to use, but we don't have to do that in this case because you're going to get all the images, all the data, and all the image data obtained for that object if we don't choose any filters. So let's do that. We're going to click search. What it's doing, it's building a list of everything in that data set for NGC-1365 right now. Here we go. Okay, so these are all the image data sets from NGC-1365. What we want to do now is choose product level 3. Okay, over here. Product level 3 is for public release. If you go back and read the documentation for the telescope, 2B is one step before public release. Product level 3 is for public release. So those are the data sets we're going to choose. Okay, now right now it's filtering that data, and it's going to leave us with the with everything that's now available. And you'll see. So the ones I chose were from C1003. Okay, you want to choose the I2D FITS. It's a FITS file format. Flexible Image Transport System is what the moniker is for FITS. It's been the astronomical standard since the early to mid 90s when the digital age, or the digital age was began to reach a certain maturity level, and you could produce reliable digital images. And the FITS file format has been the astronomical standard since about 1993. Okay, so we're going to choose this one. This is the this is the filter, the F200. This is the 2 micron image. Here's the 3 micron image, and you want to choose all the data sets within this one observing run, the 1003 observing run. Okay, so we're going to choose the I2D, 200, 300. We can choose the 335, but I chose the 360 because 300 to 335 isn't much of a change. So, and here's the 360. Okay, so what we do to acquire those, you click it, or you can just click download right here. This is the save button. You click this. Okay, it's just going to download it. It's going to take you to a download page where you can now download it. See, it's indicating here, my browser's telling me I already downloaded this. Okay, so I don't have to continue with that step. So, all right, so let's move on and take a look after we download this and open it up in PixInsight, what happens. Okay, so PixInsight's up and running. PixInsight, I'll leave all the details in the comments section below on how to obtain your own copy of PixInsight. You provide your email address to them, okay, pixinsight.com. Okay, looks like this, the website. Do you want to click licenses? Request free trial license. This is how they work this. You request a free trial license. You have 45 days, full use of the product. For 45 days, you can save images. You can, as though it was a full use license. All right, for 45 days. After that point, you have to pay, I believe it's 230 euros, which is equivalent to the dollar. I don't know. I think the European exchange rate has gone down now. So I don't think it's going to be the same equivalent in US dollars. It's going to be less. It's going to be about 200 US dollars. But this program is well worth it. Okay. Okay, or you can purchase a full commercial license, but I recommend using the free trial license to get your hands, to get used to the product, to use it, and see if you like it before you spend $200 on it. Just a little word to the wise. But I fully endorse this product. It's a great product. It's got a little bit more than average to steep learning curve, but once you master it, it's worth its weight in gold. Okay. Go back to PixInsight. All right, so we have our the galaxy data downloaded and ready to go. So what we want to do is we want to click File, Open. We're going to open Recent because I've already done this project. So we're going to click Open Recent. Here's the 200 image, the 2 micron image right here. Now this is in the FITS file format. In this particular case, the single file has 8 layers. and you're going to see it's starting to open it up now. You can see here, okay, the first of 8, the second of 8 image layers is being opened. It's working on the third one here. This has the pointing data for the telescope here. These are the coordinates for the various sections of the galaxy that were imaged. So this is the right ascension and declinations. This is the pointing data right here. Okay. The next one is the imaging data that the telescope used, that was input by the user. And here's the size of the image right here. This is a big image. It's 4,500 by 8,300 pixels wide. Okay, it's a big image. Okay, we're working on 5 out of 8. These are really big images, and it takes a lot. I'm running Mac 10.15 OS. It's available for all platforms. PixInsight is available for Mac, Windows, and all versions of Linux. Okay, so we cover all the bases with it. It's a great program. PixInsight. Okay, we're on 6 out of 8, 7 out of 8 opening. For some reason, the 2 micron image here was rather, there was a lot to it. But the other 2 don't take as long, although they do have 8 layers to the image. Okay, we're on the last one. And this is the actual image data that's in this last one. So when it finally loads, you're going to see we're going to delete the first 7 layers and just be left with the image data itself in the FITS file. Okay, here we go. So we're going to minimize this window. Okay, and here's our images here, coming up right here. Okay, so we're going to eliminate the first 7. These are layers that we used, the imaging requirements for the telescope were diverse, right? Many people are going to be using this from every part of the world, every corner of the globe. All right, so they want to accommodate as much of the you want to get as much of the quality out of the instrument that you can. Okay, but for our purposes here and now, we don't need that. So we're going to close the first 7. This grayscale data in here. Okay, here we're going to be left with this one. It has the psi right there. It says SCI. This is the scientific image. Now you're probably saying, but I don't see anything. That's because in FITS you have to apply what's known as a stretch to actually make the image available. We're going to click the stretch here, and there it is. This is the 2 micron image of NGC-1365. All right, this will be our blue image in the RGB format. Okay, as I mentioned earlier, right? So let's download the remaining 2, or open up rather the remaining 2. Open up recent image files. We're going to do the 3 micron image right now. Here we go. It's going to be, again, it's going to be 8 layers deep. We're going to delete all but the last layer. Again, we have the pointing information here, the pointing data for the telescope, right ascension and declination, in the field of view, and all this relevant information right here. With the resolution of the telescope, 0.063 arc seconds per pixel. That's quite a good resolution. Okay, here we go. So it's opened up the image. The eighth layer is done. So let's minimize this. Now we're going to do the same thing we did before. We don't need these first 7. This one right here. This is the SCI. Contains the science information or the science data. Okay. We're going to extend it. Now we're going to stretch it. Right here. This is the stretch. Okay, this is in 3 microns. This is a 3 micron image of NGC-1365. And here, the last one is the 3.6 micron image. Okay, apply the stretch. Okay, so we have our the 3 grayscale images that will become the red, green, and blue input to our RGB process. Okay. Okay, this video is accompanies a full-featured article where I go into a little bit more depth describing the RGB process. Okay, suffice it to say that use the grayscale images in 3 separate red, green, and blue wave bands to produce what they call a composite image made up of 3 separate wave bands. When you integrate them into one composite image, it becomes as lifelike as possible. Now, keep in mind, these are infrared images, and the assignment of a color is really subjective. So what I did is I adopted a similar methodology as NASA. When they process them, you assign the shortest wavelength image to the shortest wavelength color in the visible realm. For example, the 2 micron image will be assigned to the blue image that goes into the RGB composite. The green will be the 3 micron, and the red will be the 3.6 micron image. Okay, and that will become our RGB composite pre-processed image. Okay, so let's take a look. What is the next step? We want to load our processes, which are available all here. All the processes that are available to you in PixInsight are obtained right here in an unfold, all in free form here, not free form, but all available directly, or as part of a process, a full process, like astrometry, background modelization, channel management, etc. They're all contained in folders, but they're all available free form right here as all processes. Okay, so we're going to load them up. I set them aside for the ones I used most often. Okay, so we're going to load the process icons, which represent the processes here. Okay, right here. PixInsight processing right here. Okay, right over here. Okay, so the first thing we want to do is we want to register the images and star align them. So what do? We have to choose, we're going to choose what image we want as a baseline. So every image in the RGB composite, all the stars present in all 3 images will be aligned, perfectly aligned one to the other. So there'll be no misalignment going on. Okay, so what we want to do then, so we want to choose star align right here. Choose this process. All right. Before we actually execute this application, we want to select the preview, because when you do a star align process in any of these digital imaging processing programs, it's very heavy usage of the CPU and your memory. So you want to minimize that. Otherwise, it's going to take a long time. So what we're going to do is we'll select a preview of the image right here. We choose this little icon here. This is a preview. We're going to preview this right here. This section here. Okay. Now, if I were to zoom in on any one of these, we'll choose this one since we're already here. Let me zoom in on it. You can see a myriad of stars that's part of the bar with NGC-1365. The further you go in, the more stars you see. Look at the nucleus of this. This is amazing. This is a fantastic image. Look at the intensity here. Okay, up here, all this model appearance. If you go zoom in, these are all stars. Every one of these are stars, typically A-class stars, A-class and early F stars. The sun at this distance would be invisible at 55 million light years, or 17 megaparsecs. It would be invisible. The sun is not visible at this distance with this telescope, and that would require a telescope in the 10 to 12 meter class to see. In that size range, 10 to 12 meters would be required to see the sun at this distance. Okay, so those are A-class and early F stars, F-class stars. Okay, so getting back here, we want to apply another preview here to this image, and we're going to do this for all 3 of these. Okay, preview on that one, and we'll select this again, and we're going to preview this one here. Okay, so now we're going to go back. This is our baseline image. The 2 micron image is our baseline. And we're going to choose that as the reference image right over here. Okay, we're going to click View. Okay, we're going to select our 2 micron image. This is it right here. Make sure you choose the right one. That's the one right there. Click OK. All right, now, this great thing about PixInsight, these little icons along the bottom are very important. This little triangle right here is to apply the application to a particular image. This is to execute what's contained in this script. This is essentially a program operating inside the program, a smaller program that does a very specific task. In this particular case, this is a star alignment application that's part of the PixInsight. So to execute it, we would click this, but we don't want to just execute, we want to apply it. And that's what we would use this triangle over here. These features over here, this resets the whole thing, this button right here. Okay, so we've chosen this. Now what we want to do, if we want to open up the star matching section right here, we want to make sure, all right, so we're going to make sure it's set to restrict the preview only. Otherwise, it's going to examine every one of these myriad stars that are here. And it might take the whole afternoon to do that. So we're just going to do the previews. Okay, so that's all set. Restrict the preview. Okay, now we're going to apply this to the next image, not to the first one, because we're using the first one as a baseline. So we're going to drop this triangle on the image, and it's doing its thing now. It's registering the image and aligning the stars in the preview mode only. So it's just analyzing the stars in the preview, and it's going to produce a registered image. This is going to be the one that's processing now is going to be the green image. The 3 micron image is the green image. Okay, so it's almost done. Structure map, 91%. Still working. Okay, it's finished. Detecting stars. Okay, it found 11,115 stars just in that tiny little preview. Okay, it's building the structure map, detecting more stars, matching stars. So this process here is what we call the pre-processing step. We're actually just building a very base raw RGB image from which you can then apply additional processes and tweaks to hone and produce that final image that you're satisfied with. Okay, that requires another whole. The PixInsight is very, very dense and very deep and rich in what you can do with it. And this one video is not meant as a tutorial on using PixInsight. I just want to show you guys how you can actually produce your own fantastic image that's produced by NASA. Okay, you don't have to wait for them to release it. You can get this data and do it yourself. Okay, so this one is done. Okay, so now we have our blue image, we have our green image. Now we want to apply those changes. So what we're going to do is we're going to minimize this to clear up our screen here. This is going to be our blue image. Drag that down here. This is our green image, which is right here. So this is our original. What it just produced here, this is our green image right here. So we're going to stretch it. Okay, this is our green image. So we have our blue image here. We have our green image here. We're going to minimize this. When it says registered, we know that's the image we need to use. Okay, so we're going to just stack them over here, so we don't choose the wrong image. Okay, so we're going to apply this again to the red image over here. Same thing we're going to do. Okay, it's running, and this will produce, when this is finished, this will be our red image that we're going to combine to produce our RGB composite image. And from that point, we can then tweak it, improve the background contrast, do all kinds of other things. That topic is for another video. This is just intended to show you how you can actually get started with this whole process. It's fascinating, and you don't have to wait, for the engineers and the scientists at NASA. The astronomers at NASA have a lot to do, And actually, this image, this is all the data that this telescope is obtaining is available to the whole world. Okay, it's a public access, so everybody's entitled to use this. So the scientists have a 12-month period during which they can access the data free of undue coercion or duress or pressure to produce results. They have a whole year for exclusive access to this data if it's not part of the early release program. Okay, this data was part of the early release program, and that's why we're able to do this. Okay, with this particular galaxy. Okay, so this one's almost done. Apply a stretch right here. We're going to have there's our red image. Okay, so we're going to minimize this down here. I'm going to minimize the rest of these two. I'm just going to put these aside. I'm not going to close them because you never know if you may need them again. So we're going to put these over here. So anything that says registered on it, registered, good, we're good. Okay, so we're done with this. Close this. The next thing we want to do is combine the colors. We'll do that with the color combination right here. Right here, this is pretty straightforward. We're going to choose for our red image the one we just completed right here. So open this up. Not that one. So these are the choices. So the registered 3.6 micron image is the one we want to use, this one. Click OK. For the green image, it's the previous one. Registered, this is the 3 micron image. OK. And finally, for the blue image, it was the original 2 micron, the 2 micron image right here. Okay. And we want to apply these globally, so we're going to click this circle right here. So this applies these changes globally to produce one integrated composite image. Okay, it's working. Here we go. This is going to produce our final RGB image. And here it is. It's all done. It took 13.9 seconds. Okay, so let's take a look. This is our raw RGB image. We're going to apply the stretch process to it. It fits files. You have to apply the stretch. So that's going to be right here. I'm going to stretch the image. It's working. Now it's got 3 channels to work on. Okay, to build the image in three separate layers, each one representing a different waveband. And here we are. Now this is a raw pre-processed image. Okay, what we can do now right off the bat, and what I did with my final images that we're going to present later on in this video, this cropping, for example, the dynamic crop, this tool will crop out these ragged edges here. Okay, this has a greenish brownish hue. We can do something with the background. We'll close this process here. Okay, minimize these, keep the clutter down. Okay, and this is our pre-processed raw RGB image. It's going to be subject to further processing. Okay, now when you look at this and compare it to the images that I present later, you can see some similarity to this. Okay, right off the bat, let's see if we can do something here with the background neutralization. Okay, reference image is this one here. Before we do anything though, let's save the image. This is just a view. This actually isn't saved as an image. So we're going to save this as a FITS image, FITS file image. Okay. This is the default it uses, but we're going to call it NGC-1365. We're going to put raw. RGB, and today's date. Save this. Okay. Again, we're going to choose all these. We want to save all these properties of the image. You never know when you might need them later on. You could save this as a 64-bit image. I don't recommend it though. Some machines, for example, a mobile phone or some older tablets and laptops might not be able to handle the 64-bit architecture internally. So that's why I would save it as 32-bit. Okay. Right now it's writing the raw FITS file, full RGB FITS file. And then you could go back and massage this. This is the halfway point in the processing of this data. We're halfway there. You can go back, retweak it. There's a lot of steps and there's a lot of tutorials out there on PixInsight. If you use this program or download your own copy, it has a full featured suite of documentation. And I'll probably do another video on this a little bit later on. But for now, I just wanted to showcase this galaxy and let everybody know and show them how to do it, how you can produce your own outstanding images directly from this what amounts to a public orbiting observatory at the L2 point, Lagrange 2 point. Okay, so this is done. So we saved the image. We saved it. So we're going to open that image. Open. This is the view. That is the image. So let's open the view. Yeah, this one. Here it is, right here. So we open this. These files are tremendous. They're very large files. Okay. This is just opening the file. You can get a sense of what has to happen here, how big the file is, and okay, so here we go. We're going to apply stretch to this. We're going to minimize this. Okay, tuck this away here, over here. And what you can do, like a lot of image processing software, you're going to save this. We'll eventually save this as a project. Save as a project right here. And this takes a while. That takes about 10-15 minutes to save all this processing information, all these images that we saved and processed in all these intermediate steps. That gets saved into a project. So if you ever have to go back and recreate some of this, you can do that by opening up the project. By load project. That would be right here. Okay, so we're going to take a look at this. We're going to stretch this image, and this is what we're going to work from. Okay, it's going to be simple. It's going to be identical to the one we just minimized. This image 32 over here. Okay, so it's thinking and working. Okay, we want to apply, execute this. Okay, this is the first step in trying to, get rid of some of that, the unwanted background, the green, brown. Okay. Okay, evaluating background. Okay. See, it made a substantial change. See, much better. Okay, now we want to apply another stretch. Yeah, that's much better. Okay, there's another process here we can use. The dynamic background extraction. This process right here. Get rid of mine as well. Okay, we're done with this. It's a neutralization. That helped us. Okay, so there was an improvement with that right away. Okay, so what we're going to do here, we're going to calibrate. We'll choose the color calibration tool here. Yes, color calibration will help enhance the background. We'll go a long way in enhancing the background here. Okay. I'm not going to go in here and do the crop because you can. It's easy enough to see how to do that. Okay. So what we want to do is we want to preview. We're going to select a region of the image that's a representative background, right? we're going to call that a preview. Okay. Try to find a place, a region on the image where there's no stars. A good sampling of the background. Okay, so that's preview 1. The second preview, we're going to give it something to compare it to, and that's the nuclear center right here. Okay, so this is what it's not equal to. So it has something to compare and mitigate the background. Okay, we want to line it up right on the center, and we're going to, our right image is this, preview 02. Preview 02 is our right reference. So we're going to choose preview number 2. This one here. Okay. And the background reference image is going to be preview 01. Okay. Right here. Okay. And we're going to apply this. Execute it. And apply it. Okay, it's done. Looks much better. Right out of the gate, looks much better. Get rid of the previews. Now there's other additional enhancements that delete the preview. Additional enhancements to improve the contrast. Curves transformation is one such thing. Basically apply an S-curve to this. This is an RGB image, so here we're going to enhance the contrast. Okay, first, before we do that though, let's open up a real-time preview here. So this is what it will be This is what it will look like after we apply these changes. All right, so here's improving the contrast here and improving the saturation here. Apply this to the image using the triangle. Okay, the image is being applied. These changes are being applied to the image, and then you go back in there and tweak it and enhance it even more. So what we're going to do when this is finished, we're going to zoom in on the core and take a look at our new image of NGC-1365. Okay, I think it's done. Minimize it. Zoom in. What's nice about PixInsight is you can the scroll bar of your mouse you can zoom in. So there's the core. This is amazing. Here's a star forming read. This is the stars that you see here are O and B class stars, high luminosity stars, high mass, high luminosity stars. That are visible at 55 million light years. So they have to be high mass, high luminosity stars. And there's more things we can do with this image. You can tweak it even more. There's a variety of processes that we can work on. But I didn't want to get into the depth of that right now. This is just want to show you how you can get your first image and start from there and work towards building a great library of professional class, observatory class images. Okay, when we look up here, we can see the star forming arc along this is the eastern quadrant of this galaxy. These stars this is a star forming region. Okay, why is that important? Because in infrared, this is not visible light. This gas, these stars, these are brand new stars in here. Zoom in even more. Zoom in here even more. These stars, these are high mass, high luminosity stars that are still embedded in the gas left over from their formation, and that's being heated up. They're heating up this gas, and thus it's causing it to shine and in infrared light. And that's why this is important. It's an important tool for the astrophysicist and the astronomer in making assessments and further study of these distant objects. This blue circle right here is an indication of a nonlinear intensity gradient right at the middle. What that means is that the intensity increases sharply as we approach the center. This galaxy is host to a rapidly rotating 2 million solar mass black hole, and that would be right here. Okay, right at the center. Okay, and why is it in blue? Because blue is the shortest of the wavelengths, and that would be the highest intensity in terms of what would be coming from that black hole. Okay, that's our preview, and here's our image. Zoom back out, zoom in close. Look at how that just jumps right out at you. So this is our first pass. Data just downloaded from the James website. You can jump right in and start producing these amazing professional observatory class images. You can see this dark, the gas and dust swirling in towards the black hole here. Okay, so there we go. So we're going to wrap it up there, but there's a lot more you can do with this. Now before we go, we want to save this image. Also, you want to run the crop tool. This is just the first pass to give everybody a flavor for this and a sense of what you have to do. Screen transfer function is actually required here to save these images to the actual. So what we're going to do here, okay, now we're going to save it. Save. That's it. We have our first image. And from here, not everybody can read a FITS file. So in order to share this with the world and the community, what you're going to have to do is save this as. You can do that here in PixInsight. Okay, it's done. I want to save as. For now, we'll just save it as a JPEG. It's pretty much standard everywhere. Save it as a JPEG. Now it's going to ask you, I choose the highest quality for JPEGs. At 100, quality is 100%. I'm going to save it. JPEG's the smallest footprint. And then you can share that. Not everybody has the ability to read a FITS file. So everybody does have the ability to read a JPEG. And the JPEG is going to be big for JPEGs. Okay, so now that that's done, let's just open it up and make sure it is what we expect. Click open. We want to choose the JPEG we just created. And here's our JPEG. Close all these windows here. Okay. So the way this works, you have your FITS file here, and all the changes and all these processes that we use, you have to apply it to the image. This actually looks quite good. Okay, this is our JPEG right here. See, here's our JPEG. Here it is, JPEG. That's our JPEG, right? So what you would do now, this is the image you would share with the rest of the world. You save this FITS file because not everybody has the ability to open up and process a FITS file. But this is an incredibly good image just for a first. How long did we spend on this? 15, 20 minutes, maybe 30 minutes. This is your first pass. You went to the mass site, you downloaded your data, you star aligned, registered the image, created an RGB integrated composite, saved it, processed it, and now here we go. We have our first image, okay, through PixInsight. Okay. But I was starting to say, yeah, you have to use the screen transfer function to take what you see on the screen and transfer it to the actual image. Now, when we first set this up, you actually have to choose here in the histogram information, this process right here. Originally, you have to actually choose the image you're working on. This screen transfer function interprets in RGB and luminance format what it sees in the image, and that gets transferred to the image itself. Otherwise, this is just an internal view. We didn't transfer that view to the actual image. The screen transfer function does that. Okay, so this is, if we look at the histogram, this is what it looks like. Here's our red, green, and blue integrated image. Okay, now what you would do, I'm not going to do this over again, you would basically take this triangle and you just drop it on here on the original FITS image, save it as a JPEG, which is what we just did. And this is because I did this, so this has been done already, right? So this is what we did previously in a previous step. We're not going to do it again, otherwise we'd overwrite what we just did. We save that as a JPEG, which is right here. Now we can zoom in. Let's zoom in on this. Just choose this image and we can zoom in. You have this stunning detail that we had before. You can see these individual A and F class stars at 55 million light years, or 17.1 megaparsecs. Parsec is 3.26 light years. So those terms are more or less interchangeable. Okay, but we here have a star forming region right here, right above the core. That star forming region is no doubt the result of the turbulence and the inflow of gas and material into this rapidly rotating 2 million solar mass black hole that's triggering the star formation. And this is known as an active galaxy. NGC-1365 is known as an active galaxy. Active galaxy is a characterization of a galaxy that's host to an active black hole at its core. And the effects of that black hole cause prodigious amounts of star formation, which is what we see here. Okay, so this is actually one of the known active galaxies close by. This is not that far. It's only 55 million light years, which is cosmologically not that far away. Okay, so there we go. We can share this image with the world, and we're good to go. I hope this exercise in PixInsight was informative, and that you can use it. And please feel free to like the video, share it, tell your friends about it, and any comments or questions you have about what we did here today, or in general about PixInsight, please do post your question or comment in the section below.